let's consider Q adjoint root 2 over Q. So now, okay, Q adjoint root 2 is a splitting field, right? So Q adjoint root 2 is the splitting field of x squared minus 2 over Q. Okay, so you adjointed one square root of 2 to Q. How do you know that this is the splitting field of that polynomial now? Well, the point is that, look, this thing, once you adjoin one root of this, the other root you get for free, right? This will be now x minus root 2 times x plus root 2. Root 2 being one of the two square roots, the other one will be minus root 2. Both square roots now will be in there. This is a splitting field of x squared minus 2 over Q. And now, okay, so, well, and now this polynomial there. So by the way, if you're working over characteristic 0, this condition that the irreducible factors have to be, when you want to apply this result here, the number of elements of the Galois group of the splitting field equal to the degree of the extension, when you to apply that result, okay, so in general you need the irreducible factors of your polynomial to be separable, but if you're working over characteristic 0, that's guaranteed anyways. Remember, every reducible polynomial over a field of characteristic 0 has no repeated roots. So, well, now we're working over Q, so we don't have to worry about that. Now, okay, this is a splitting field over Q, and that implies that the number of elements of the Galois group of this field over Q, so the number of automorphisms of this field which fix Q, is equal to the degree of the extension Q root 2 over Q. Right? And now this polynomial is irreducible by Eisenstein criterion, let's say. It's overkill, let's just say, by Eisenstein criterion. Now it's irreducible, so this will be adjoining root 2 to Q. We're going to get an extension of degree, well, the degree of that polynomial degree 2. So this Galois group has 2 elements. Right? Okay, so these are elements of the Galois group are automorphisms of Q adjoint root 2 which fix Q. And there's 2 of them. Let's see what they are. See, okay, so what are we looking for? We're looking for maps from Q adjoint root 2 to Q adjoint root 2 which fix Q. By the way, fixing Q is guaranteed, right? Any ring homomorphism from here to there would have to fix Q. But let's keep it explicit. So automorphisms that fix Q, now isomorphism from here to here which fix Q. Now, well, use lemma 50 of your textbook. To get maps from here to this field, okay, so you want to extend the identity map on Q to a map from here to there, right? Well, root 2 is a root of the polynomial x squared minus 2, right? Now, you have to send root 2 to a root of this polynomial in there, right? Remember, you have to send root 2, alpha, root of this polynomial f, to a root alpha prime of the polynomial, of this polynomial. If I call this map sigma, I have to send alpha to a root alpha prime of if this is sigma, of sigma star of this, right? Sigma star of this is just itself. Sigma is identity. You have to send root 2 to a root of this polynomial in there. Well, it's got 2 roots there, root 2 and minus root 2. You have to send root 2 to one of those 2. And remember, by lemma 50, there's going to be a unique extension. unique isomorphism from Q adjoint root 2 to Q adjoint root 2, fixing Q, which tends root 2 to root 2, and there's going to be a unique isomorphism which tends root 2 to minus root 2. Remember, for any choice of alpha prime, root of sigma star f, there was a unique homomorphism extending sigma, sending alpha to alpha prime, right? That was lemma 50. So there's going to be, so there's two homomorphisms. There are two homomorphisms. They will be isomorphisms. So let me just write here isomorphisms. There are two isomorphisms from Q adjoint root 2 to Q adjoint root 2, which fix Q. But again, that's automatic. So let's not write that down. There are two isomorphisms Q adjoint root 2 to Q adjoint root 2. One sends root 2 to root 2, and the other sends root 2 to minus root 2. Let's just give them two names. So let's call this one maybe sigma 1. So this one I'm going to call it sigma 1, and that one I'm going to call it sigma 2. Or if you don't mind, sorry, let me erase this and instead 1. Yeah, so yeah, let's keep that as that. And then sigma 1 being the one that sends root 2 to root 2. This is given by the following formula. Well, remember, any element here, so 1 and root 2 form the basis of this guy over Q. So sigma 1 of A plus B root 2. Every element of this field is of this form for some A and B over Q. For some unique A and B over Q. Sigma 1 of that, if sigma 1 sends root 2 to root 2, well, this would be now A plus B root 2. This is A. So sigma 1 is just identity. And then sigma 2 of A plus B root 2 is equal to, well, sigma 2 now sends root 2 to minus root 2. So A minus B root 2. That's sigma 2. Okay? And then the Galois group there, the Galois group of a Q adjoint root 2 over 2 consists of these two maps. Sigma 1 is just identity, and then sigma 2 is this guy here. So why don't we right, so the Galois group of Q adjoint root 2 over Q has two elements, one being identity, the other one being the map that sends A plus B root 2 to A minus B root 2. Here A and B are rational numbers. Okay? Very good. Sorry? Yes, very good point. Very good point. So, so she's asking, she's making an interesting observation. So let's write this as a remark. Any degree 2 extension is a splitting field. Right, so here, so let's say K over F, this has degree 2. And the claim is that K is going to be the splitting field of some polynomial over F. Let me make sure that we don't lose the camera. See why? So let's see what's the reason here. Well, okay, so K over F has degree 2. So K is not equal to F. Let's take something in K that is not in F. So let alpha be in K, but not in F.